extruded like toothpaste.
Who would do this to an automobile?
How does industry control and use great force?
Industry on Parade. Peabody Award winner for public service, produced on film each week by the National Association of Manufacturers.
A block of marble being broken loose in a quarry. The job takes precise timing. A rough diamond about to be cut into gemstones. Unless the cleaving is done perfectly, the blow of the hammer would shatter the diamond to bits. An ingot of white-hot steel being shaped in a forge press. Though thousands of tons of pressure are used, that pressure must be applied for just so long and in just the right place, or again the loss could be tremendous. Throughout manufacturing, force is applied in hundreds of ways, as we're about to see in this report on impact and how industry employs it to shape, change, and improve raw materials, transforming them into products with an impact of their own on our standard of living. At Jones and Laughlin's Pittsburgh plant, a heated billet of rugged carbon steel is prepared for a press that will ram it through intricately shaped dies, transforming it in seconds to all sorts of odd-shaped machine parts that once required extensive and costly individual fabrication. The hydraulic ram pushes the billet into the die with a force of 1,000 tons, and instantly it emerges in a new form. Steel extruded like toothpaste squeeze out through the mouth of a tube. As a matter of fact, toothpaste tubes themselves are extruded. Metal that goes in as slugs emerges as tubes faster than the eye can see, each one being converted by a single blow. Here's a better look in slow motion animation. On impact, the metal will fill the die, then flow up between the two parts to become the sides and one end of a hollow shell. That's impact extrusion, taking place in less than a second. New cars get their shape from powerful presses, and other presses help dispose of them in the scrapyard when their useful life has ended, squeezing them into neat bundles, all set for the furnaces in which they'll be melted down on their way to becoming useful articles once again. Here's what 2,500 pounds of pressure per square inch can do to an automobile. The tremendous force of a pile driver makes short work of heavy construction jobs, helping to build the foundations of the biggest buildings. And as a building rises above the ground, the lighter blows of a power hammer on flame red rivets help bind the framework in place.
Other kinds of fasteners can be driven into metal, concrete, even rock, by the impact of a small explosive charge designed for use in a device developed by the Powder Power Tool Corporation. Just insert the powder charge and pull the trigger to get a bang out of building a house. Long ago, industry developed some pretty efficient nut-cracking machines, but it wasn't until high-voltage electricity was enlisted for the job that the processors were able to control the operation so precisely that virtually all the nut meats would come through intact. 25 shells are exploded every second. Millions of times more powerful than the explosive nutcracker, the dynamite used in mining can free ore-bearing rock so economically that even low-grade deposits are becoming worthwhile. The added impact of powerful crushers also is an important part of mining processes. Often, industrial researchers create tremendous forces as an aid in testing products that must withstand natural and accidental blows. Here, a test window survives an artificial hurricane. And now preparations for ramming one freight car into another in an effort to show Union Pacific Railroad employees what the jolt can do to the cargo. One side of the demonstration car is made of plexiglass to permit observation of the cargo at the moment of impact. The tests also permit close study of various methods used in securing various items. Here goes, and here's what happens. At only 7 miles an hour, a sudden stop shifts the oil drums 47 inches. A graphic demonstration to the freight handlers that the watchword must be, easy does it. Vehicles can be stopped more safely today because industry puts their parts through tortuous tests. This one simulates the impact on tires of an airplane landing. These men are metallurgists about to compare the quality of a new kind of iron with an older variety. Under impact, ordinary cast iron snaps. They've added magnesium to the next sample called ductile iron. And now they subject it to an identical blow, proving without doubt a very measurable improvement. Much more complicated, the research equipment in this room in Everett, Massachusetts is called a shock tube. It was built by Avco Research Laboratory to duplicate, on the scale model of a rocket's nose cone, the shock, heat, and turbulence encountered when a missile re-enters the Earth's atmosphere at 18,000 miles an hour. Inside the tube, the impact on the metal sample will last only a few millionths of a second, but long enough to tell science what it needs to know. Here's how such tremendous force is developed. Behind this thick metal plate, highly volatile gases will be compressed and ignited. The diaphragm has been scored to give way at a predetermined pressure. When the diaphragm bursts, a shock wave will flash down the tube and hit the sample under study at 25 times the speed of sound. Now the rear section of the tube is loaded with gas under great pressure, pressure held back by the diaphragm. On the other side of the diaphragm, a vacuum has been created, almost all air withdrawn. The experiment is about to begin with ultra-fast cameras ready to record the results. All set? Here we go. Externally, nothing happens. But inside, these are slow-motion pictures of the shock wave, and this a still picture as it hits the sample. The shock wave is dissipated by an expansion chamber, and the experiment that took many hours to set up is over in a fraction of a second. They remove the ruptured diaphragm, which helped reproduce the conditions that someday, perhaps, will be encountered by rocket ships coming back from the moon. Now we're at Hurricane Mesa in southwest Utah, where a dummy packed with instruments is made ready for a ride in a rocket-propelled sled from which it will be ejected suddenly at a speed of 1,500 miles an hour. The test dummy will help researchers find out how better to protect the people who face the hazards of similar impact. Down the dummy floats, filled with information that will help science save many lives. Tests like those we have seen have produced dozens of useful results. Among them, the equipment in use here, permitting high-speed airplanes to land on very short runways. The plane will engage a steel cable, something like that on a carrier deck. Only this one is linked at each end to pistons in water-filled pipes that parallel the runway in such a way that the force of the landing plane is absorbed and controlled, permitting a safe stop in only 100 yards, even for a jet.
The arresting gear is a good example of the many products devised by industry to control impact. While the creation of mighty jolts is useful in many ways, as we have seen, methods such as this for lessening effects of sharp, sudden shocks also are industry's concern. Engaged by the plane, The cable tugs at its water-encased pistons, which help a short landing strip do the work of a long one. All-American Engineering Company, the same firm that developed the water squeezer landing system, also has put the winch to work on many problems involving the absorption of energy and the control of impact. For testing and development, the winches haul heavy loads up and down a tower, simulating the stresses and strains encountered in actual use. The test setup will handle up to 30,000 pounds, and it has helped the engineers develop some remarkable equipment, like that used on fast-moving speedboats to rescue pilots or frogmen from dangerous waters. As the speedboat comes alongside, the men grab large rings attached to a winch, which absorbs the shock, then pulls the swimmer out of the water. The Frogman pickup is a spectacular demonstration of just one of countless new products developed in industry's continuing quest for new ways to control impact on one hand and to utilize it on the other. It's a quest that adds to industry's own impact on our economy through the creation of new products, new opportunities, new jobs. And now, get set for the rescue of a man from the ground by a conventional airplane that will snare a nylon rope suspended across two upright bars. The rope is attached to a special harness worn here by engineering assistant Harry Conway, who has volunteered for the test, the first ever to be attempted at high speed. Since he's worked on the development of the system all along, he has no doubt about its ability to absorb the tremendous shock and to lift him safely to the airplane that's about to roar over him. No mere stunt, the test will help prove rescues of this type are practical. And here is proof. Motion pictures in slow motion of the approach, the contact, and the actual pickup of a man by a plane flying 150 miles an hour. A dramatic example of industry's victory over impact.
American industry, builder of a better tomorrow, has presented Industry on Parade, a service of the National Association of Manufacturers.